Right, so today we are discussing a velocity diagram related problem, right? So now I will explain you the configuration diagram, right? That is the most primary action that we have to do, right? After sketching this only, we can proceed to the velocity diagram. So let me explain. So now here we have the input crank OA, right? The crank radius is 60 millimeters. This length OA is 60 millimeters, and based upon the primary rotation of this OA, right, uh, the crank PQ is made to rotate, right? In other words, we are going to consider crank radius OA as an input to crank radius PQ, right? So then here O is the crank center, and here when considering crank PQ, P is the crank center for the crank PQ, right? And according to this problem, the crank OA rotates at 800 rpm in clockwise direction, right? So this crank OA rotates in the clockwise direction at an rpm of 800, right? So it is mentioned there. And then as the output, the crank PQ rotates in the anti-clockwise direction, right? At an RPM of 400, right? So that means in order to get 400 revolutions per minute from crank PQ, right? So you have to give 800 revolutions per minute of revolutions on crank OA as the primary input. So then again in this problem it is said that this end A of the crank OA, right, because now this point is the end of the crank OA, right? So that is extended until the point B, such that we can have another link of length AB. Now this is the link AB, right? This is A, this is B, and the length of the link AB is 70 millimeters. Okay, right. Because in the problem it says that two supportive links are defined as AB of length 70 millimeters and also QB of length 80 millimeters. That means there is another supportive link of length QB, see QB, that is formed by extending the end Q till it intersects the point B, where this QB length is 80 millimeters, right? That means this link AB and this link QB meet at a common point, so that common point is B, right? Now when considering the original position, right, so when we are going to sketch the configuration diagram, we have to consider the original position, right? So now the status or the state of the crank OA is in such a way where it makes 40 degrees with the horizontal center line of the crank center O. This is the crank center O, right? So this is the horizontal center line of the crank center O. So it makes an angle of 40 degrees with the horizontal center line in the first quadrant, because this is the first quadrant. You know what is the quadrant, right? Quadrant 1, this is quadrant 2, this is 3, this is 4, right? Okay. And with respect to that position, so when you are going to consider the state or the status of crank PQ, it is making an angle of 30 degrees, right? So at that same time, right, at that same instant, the crank radius PQ is making an angle of 30 degrees, see, 30 degrees in the first quadrant, where the angle is made with respect to the horizontal center line of the crank center P, right? And what else? What are the other information you need? Okay, right. In addition to that, we have three pistons, right? So that are defined as piston D, piston T, and piston S, right? Where piston D follows a vertical path, piston T also follows a vertical. Okay, so now let's see what are the data that we have considered. Crank, now I'm again reading the problem, right? Crank OA radius 30 millimeters is defined as the primary input to the crank PQ of radius 60 millimeters, right? I think I mentioned the length of this crank PQ is 60 millimeters, right? Then OA and PQ are linked, right? So that means this OA and PQ are linked by several linkages, right? Okay, like several supportive links. That means here you can see in order to link this crank radius PQ, basically they have used this link AB and again this link BQ. See, this is letter B and this is letter Q, right? Okay. Then rotation also I have told you what is the rotation, right? Now again another important detail is there. Crank center P of PQ, this crank center P of PQ is positioned 80 millimeters below the crank center. Okay, so that means this crank center P is positioned 80 millimeters. See, this 80 you have, so this length is 80 millimeters, right? Right. So crank center P of PQ is positioned 80 millimeters below the crank center O of the crank OA, such that the distance between the vertical center lines of the crank O and crank center P is maintained at is 30 mm. Alright, so that means let me use another color, right? What color shall I use? Okay, let's say brown color. So now this, here you can see the vertical center line. See this one, this is the vertical center line of the crank center O, and this is the vertical center line of the crank center P, right? So the distance between the vertical center line of the crank center O and crank center P is maintained at 30 millimeters, right? This distance is 30 millimeters, right? Okay, so that is also now here if you consider this piston S, see piston S. Now piston S follows a horizontal path, right? So this is horizontal, right? This goes horizontally. So distance between the path of the piston S and the horizontal centerline of the crank PQ is made. That means in this crank center P, this is the horizontal centerline of the crank center P, right? I'll sketch like that. And this is the horizontal path of the piston S. So the distance between this horizontal center line and this path is also what is that, 30 millimeters, right? Okay. So now a kinematic link, right? So because in order to transfer the motion you need to have a kinematic link. So now that kinematic link is formed by extending the point A up to B and Q up to B. So now you can see they clearly meet at a common point B, right? So length also I have defined now, right? So there is a link SR of length 100 millimeters, where this QR is 20. Okay, that is also okay. And the next information, the piston D is connected to the point C on the supportive link AB such that AC is 40, right? Again the same thing. Now we know that piston D follows in a vertical path. Piston D is connected by using the help of a link DC, right? DC, right, to a point C on the link AB. Now when you are going to consider the link AB, there is a particular point that is defined as C, where the distance AC is 40 millimeters, and it is that point C is the point where the piston D is connected with the help of link DC, right? See, DC. So what is the length of DC? Have they specified the length of DC? Yes. AC is 40 millimeter. That means this A to C is 40 millimeters. So the length of link CD is 40. This length also 40. Right. See, you can see this dotted line, this vertical path, right? So the distance between this vertical center line of the path of piston D, right, and the vertical center line of the crank center O, right? So this is the vertical center line of the crank center O. So the distance between these two vertical lines is maintained at 30 millimeters, right? Okay. And also there is another piston called T, right? So this piston T also follows a vertical, see, this piston T follows a vertical path, see, you can see like that, right? So the distance between this vertical center line and the distance between the vertical center line of the crank center O is 110 millimeters, right? Here 110, right? Because it is mentioned piston T 110 millimeters, right? Because now this is how it is mentioned. The distance between the vertical center line of the crank center O of crank OA and the vertical path of the piston D, that is already done, is 30 millimeters, and that for piston T, that means as according to the same definition, such distance for piston T is 110, right? Right, okay. So now let's sketch the configuration diagram, right? So in this problem, we are given several information, right? Information 1, 2, 3, 4, like that. So let's focus each and every information one by one, right? Okay, so information number 1, crank OA of radius 30 millimeters is defined as an input to crank PQ of radius 60 millimeters. And crank OA rotates at 800 rpm in the clockwise direction, while crank PQ rotates at 400 rpm in the anti-clockwise direction, right? Okay, so now basically we have said that our major input is crank OA, right? And its length is 30 millimeters, and it rotates in the clockwise direction. The RPM is 800 RPM, okay, and crank PQ is the output, right? Crank PQ, which is the output of crank radius 60 millimeters, and it is rotating at 400 RPM in the anti-clockwise direction, right? Okay. And the next information, crank center P of PQ. That means if you consider the crank radius PQ, right, the crank center is P, right? And also if you consider the crank OA, right, this O is the crank center of crank OA, right? Crank center P of PQ is positioned 80 millimeters below the crank center O, and the distance between the vertical center lines of the crank center O and P is 30 millimeters, right? Carefully read. After that I will sketch. When considering the current angular position of crank OA, crank OA is turned 40 degrees with respect to the horizontal within the first quadrant. That means you know about quadrants, right? This is x-axis, y-axis. This is quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? So you know that. So making 30 degrees with the horizontal in the first quadrant means this is the quadrant, making 30 degrees with this horizontal, right, in first quadrant, right? So that's a simple thing, okay? It's not hard. That is how you have to read the information, okay? I think I told you that when considering the current angular position, crank OA is turned 40 degrees with respect to the horizontal in the first quadrant, while that of PQ, right? So as according to the same way, if you're going to consider the crank radius PQ, right, it is turned 30 degrees with respect to the horizontal, right? So now we can sketch that, okay? So now let's see how I am going to sketch it. So now in this problem, crank OA is the input, right? So you don't need to worry about the position of the crank center O because that is the input, right? So let's consider this point O is the crank center of the crank OA. What is the angle? Angle is 40 degrees with respect to the horizontal. So this is the horizontal. So measure 40 degrees, right? Then you have to sketch or you have to draw this crank OA, right? This crank OA. What is the length? The length must be 30 millimeters, right? Because I will write it here. OA is 30 millimeters, right? So now in order to sketch the configuration diagram, you will need the compass, right? Measure 40 degrees and measure 30 millimeters to the compass, and then what you have to do, you have to intersect this line, right? Because that is the usual way of drawing. Just draw a larger line, right? Then measure 30 millimeters and sketch a curve, right? So that intersection point will be the required length, right? Or else you can directly draw it. So now this is our crank radius OA, right? Okay. So now okay, I will see the next information. Now what is this line? So that is the horizontal center line of crank OA, right? So like that, like a horizontal center line, you also have a vertical center line, right? So no problem. And it is said that now if you are going to consider the crank PQ, right? So PQ may be somewhere here, right? The crank center P is 80 millimeters below the crank center O. So measure 80 millimeters from here to there. Let's say like here, right? Okay. So this distance is 80 millimeters, right? Okay, right. And the distance between the vertical center line of the crank center O and crank center PQ, that means in order to locate the crank center P, you need to have two coordinates, right? So one coordinate is okay, it is 80 millimeters below this one, and the distance between the vertical center line. So here we have one vertical center line and this is the other vertical center line, right? So I think now it is okay. 80 millimeters below there, then locate up to here, right? So what is this? So this is the crank center P. What is this distance? 30 millimeters. 30 millimeters, okay, right. 80 below and 30 here. So now this is the crank center P. What is the angle? Angle is 30 degrees, isn't it? Yeah, 30 degrees. And what is the crank length? 60 millimeters. Okay, so let's sketch 60 millimeters there, right? So this is PQ, right? Okay. I will sketch it nicely. Right? PQ, right? This is the crank radius PQ, and that's okay. Have you considered all the information? Yes, I think these information I erase, right? Otherwise, if there are a lot of information on the board, it will be a bit difficult. This dotted line, okay, let's keep the dotted line. Right, that's okay. Okay. Right. What are the other information? Right. Right. So now the next information, 3 pistons are defined by D, S and T. Okay, so now there are 3 pistons in this system, D, S and T, where piston S follows a horizontal path while other 2 pistons follow a vertical path. Okay, so now we have 3 pistons, D, S and T. Piston S goes in a horizontal path, right? All other pistons, that means piston D and piston T, right, they follow a vertical path. Okay, right. So now what's the next thing? So now you need to know the coordinates, right, in order to locate the pistons. The distance between the path of piston S and the horizontal center line of the crank PQ. This is crank PQ and this is the horizontal center line of crank PQ, right? And the distance between the path of piston S and the horizontal center line of the crank PQ is 30 millimeters, right? Right. So I told you that piston S follows a horizontal path, right? So it goes like this, right? But you don't know whether it is above the center line or below that, right? So it is specified the distance between the path of piston S and the horizontal center line of crank PQ is 30 millimeters below the horizontal center line of the crank center P. Right. So measure 30 millimeters below this horizontal center line. So this distance is 30 millimeters. Right. Then sketch a horizontal line because still you cannot locate the piston. Right. So piston S goes like this. Right. Still you cannot locate that. So please wait. Okay. We'll focus the problem. Right. So 2 supportive links are formed by extending the end A of crank OA and by extending the end Q of crank PQ, that are defined as link AB of length 70 millimeters and link QB of length 80 millimeters respectively, right? Okay. And point B is formed, right, with the intersection of the link AB and QB, right? So now previously I have taught you, here we have link AB and here we have link QB, right? So now link AB and link QB intersect, right? And ultimately they form end, or ultimately better say point, right? Because that is an intersection, right? So better say point. So ultimately it will form the point B, right? And also it is very specified in this problem, point B must be positioned to the right of end Q and end A. What is end Q? Here. What is end A? There. Anyhow, point B must be positioned to the right of this end. So definitely if the point B is on the right hand side of end Q, definitely it must be on the right hand side of end A also, right? So that is also specified, right? So now the next target is how to sketch that. Again you need to take your compass, right? Now measure 80 millimeters, right? And use this center, right? Keep the other end at here. Measure 80 millimeters and sketch a circle, right? And again measure 70 millimeters and sketch a circle, right? Okay. So you have to sketch a circle of 80 millimeter radius, okay? Okay. Right? Now this is the circle of radius 80 millimeters. Then again sketch another circle having a radius of 70 millimeters, right? This is end, so the radius will be like this. Right? So now this is the circle of radius 70 millimeters, right? Okay, so now let's say this is the circle of r equals 80 millimeters. This is the circle of r equals 70 millimeters. Okay, so now here there are two intersections, right? One intersection here, other intersection is here, right? So now in this problem it is very clearly specified that the point B must be to the right of end A and end Q. That means definitely point B must be here, right? It's not a big deal, okay? So then complete this link, right? This is a very simple problem, right? 80 millimeter length, 70 millimeter length, right? So these problems are very easy now, but the fact is how you sketch it, right? So I think it's better I will erase all the unnecessary parts, right? Now this is the path of piston S, right? So piston S goes like this, right? Like that, but you can specify it, right? So now we are going to specify that. So anyhow, this is the path of piston S because it is horizontal. Now carefully focus. The piston S is connected to a point R. Anyhow, piston S is there. It is connected to a point R. Piston S is connected to a point R on the link QB. Now this is the link QB. It is connected to a point R where connected to a point R on the link QB such that QR is 20 millimeters. Okay. So now measure 20 millimeters. Let's say 20 millimeters is here. So this is point R, right? Because point R is 20 millimeters from point Q. So this is 20 millimeters QR, right? So by using another supportive link that is defined as RS, there is another supportive link that connects the piston S to the link AB, right? So how to sketch that? Very easy. Measure QR first, measure the length of QR first, no problem. So you know the point R is here. Then what is the length of that link that connects the piston? That is 100 millimeters. So measure 100 millimeters, right? Measure 100 millimeters, then sketch the circle. So let's say it goes like this, right? Like that. So what is this radius? Because now radius is the distance from the center to any point on the circumference, right? So this is 100 millimeters, okay? Because now there is an order on how you sketch. First locate R, then from the point R, again use the compass, measure 100 millimeters, right? And intersect by using that
circumference, by using that circle, intersect this horizontal path, right? So where you intersect this horizontal path is the current position of piston S. You got it? Right. Now this is our piston S, right? This is our piston S, right? Because piston S is connected to this link QB with the help of the link RS, or you can call it SR, right? Right. This is S, this is R. RS, right? Okay. Piston D is connected to a point C on the link AB such that AC is 40 millimeter. Okay, so now first locate AC. What is the length AC? 40 millimeters. So measure 40 millimeters, maybe 40 millimeters, let's say from here to here, right? So now this is point C, A to C, right? So what is A to C? 40 millimeters, right? Okay. So now when you are going to maintain the distance between the vertical center line of crank center O and the vertical path of piston D and the vertical path of piston T, there should be the specified side, whether left side or right side, but luckily it is on the right side. So if you consider for the piston D, the distance between this vertical center line and the path of piston D is 30 millimeters. So measure 30 millimeters from here, then sketch a line like that. Okay. So what is this line? This line is the path of piston D. Again, in the similar manner, again measure 110 millimeters. Okay, so let's say 110 millimeters is there. Right? So okay, so the distance between this vertical center line and the path of piston T is 110. Okay, so it goes there, right? What is this? This is the path of piston T, right? This is the path of piston T. I will erase other information, right? So this is the path of piston T, but still you don't know at what exact position the piston T is, right? Okay, no problem. Shall we complete piston D first, right? So what is the next thing you have to do? It is set the length of the link CD. It is 40 millimeters. So measure 40 millimeters. Keep one into there. Then sketch a larger circle. So let's say that circle intersects there. So again you need to get your compass. Length of the link CD is given as 40 millimeters. So measure 40 millimeters. Keep it there and intersect this path. So let's say the intersection happens there. So this is the point where the piston D is, right? Yeah, we got it. Because this is the link CD, right? This is the link CD of length 40 millimeters. Got it? Piston T is connected to the end B with the help of the supportive link TB of length 40 millimeters, right? So they are using a supportive link of length 40 millimeters that is defined as link TB, right? What is the length? 40 millimeters. So no problem. Measure 40 millimeters, keep one into there, then intersect this path, okay? Because now this is the vertical path of the piston T, so intersect there. So let's say the intersection happens there, right? This is how you are going to sketch the circle, right? Circle of radius 40 millimeters, so intersection happens there, right? So now this is the piston T, so piston T is here, okay, right? Right, okay. But there is a problem, okay? That is also specified in the problem, right? Because now you are going to measure 40 millimeters and you are going to intersect this line, right? You are going to intersect this line. So there are two possibilities for this intersection, right? The intersection can be either here or either there. And there is a problem. But luckily in this problem it is specified that, okay, so again it is specified, right? The point T, right, or in other words the nt of the link bt is below the point B, right? Because there are two possibilities for the position of this point D, because it can be either above this point B, right? Because you are going to measure 40 millimeters and you are going to intersect this vertical path, so that intersection point T can be either above the point B or below the point B, right? So in this problem it is specified that the point T, right, of the supportive link TB, right, is below the point B, right? That means point T must be below this point. So the intersection must be there. That means not this intersection, because this is also an intersection BT, but you cannot consider this one because it is specified that point T is below the level of point B, right? Okay, so that's the vertical path. Okay, so TB is the link that connects this piston, right? T. So TB, right? So TB is the link that connects the piston T to this end, right? In order to form that kinematic link, right? Or this kinematic system, right? Okay, so that's it about the configuration diagram, right? So I have explained you all the steps in detail, right?
Right, okay, so now we will focus how to sketch the velocity diagram, right? So look at this crank OA. This crank OA is rotating in the clockwise direction, right? I will sketch the crank here. So here we have crank OA and it is rotating in the clockwise direction. If so, there will be a tangential velocity at the end A, where the direction of that tangential velocity is perpendicular to this crank. It's perpendicular, right? And that tangential velocity we define by using this notation, that is VAO. That means tangential velocity at the end A with respect to the center O, which is at rest. Okay, and that equals crank radius multiplied by the RPM, right? So that means the crank radius is 30 millimeters multiplied by the RPM is 800 revolutions per minute. So that means 800 multiplied by 2 pi divided by 60. So what is that value? 2513.3 millimeters per second, right? So now this velocity we will denote by a line of 40 millimeters as a scale, right? So higher the scale, the accuracy of the velocity diagram will be higher, right? Okay, so now let's get that. Now so now this is our configuration diagram, okay, right? So we have this crank OA, the tangential velocity is perpendicular to this along this direction. So let's get that, right? I hope you can see, right? O, simple A, right? Arrow there, right? So what is the length of this velocity component? That is 40 millimeters, right? So this is the, that means this denotes the tangential velocity, right? Okay, now this O is the center of the crank, right? The center is always at rest, right? Okay, so now focus the next crank, which is crank PQ, right? So now this is crank PQ. Okay, so now in this problem it is very specifically said that this crank PQ is rotating in the counterclockwise direction. That means the tangential velocity will be along this direction, right, where it is perpendicular. So what is the value of that? So we define it, the tangential velocity at the end Q with respect to the center P equals the crank radius 60 millimeters multiplied by the RPM 400 multiplied by 2 pi divided by 60. So that also will be the same value, 2513.3 millimeters per second. So we will denote this by a line of 40 millimeters, right? So now see, this is the crank PQ.
So as it is rotating in the counterclockwise direction, the tangential velocity will be in this direction, which is perpendicular to this crank. So now what is the crank center P, right? So now crank center P is at rest, right? So we do not need a separate point to denote the crank center P, right? We can use the same crank center point, right? That means we can use the same point that we use to denote the crank center O when we are going to denote crank center P also, right? So the same point, right, can be shared to denote the crank center P, right? Because it is at rest, right? P. So the tangential velocity is perpendicular to that in this direction, right? So carefully sketch perpendicular to that. So it should be 40 millimeters, right? So this is PQ, right? In the velocity diagram, better use simple letters, right? So this is PQ, right? So again, I'm telling this point is shared by both the crank centers P and Q. Okay, so that is okay. So now focus this end B, right? So this end B, so how it is formed? Here we have the crank PQ, right? This Q is the end of the crank PQ. So this link QB is formed by extending this Q. And here this link AB is formed by extending the end A, right? Okay. So now this is also like a crank, but actually this AB that you have here is not a crank, that is a link, right? And here what you have as QB is not a crank, that is a link, right? QB link and AB link, right? But the problem is, now I will sketch the link AB, right? So now when you're going to consider link AB, you don't know the specified direction of rotation. It can either rotate in this direction or either that direction. You don't know. So that means you can tell one thing, whatever the direction that it rotates, the tangential velocity component at the end B, that is perpendicular, but the specified direction is unknown. So no problem, right? So now here we have link AB, right? So definitely there will be a tangential velocity at the end B, right? So that tangential velocity we define by V simple B A, right? That means tangential velocity at the end B with respect to the center A. That means when you are going to consider this link AB, we can consider end A as the center, right? Okay. So now AB. So this is the perpendicular direction, right? It should be perpendicular, right? So project that perpendicular length to your velocity diagram, right? Perpendicular, but you don't know the length, you don't know the direction. So let's use the pencil, right? Anyhow, it should be perpendicular. So let's sketch like that. Okay, right. And now consider for the link QB also. Now when you're going to consider the link QB, right? So I will sketch link QB here, right? This is a link QB, but the direction is unknown because it is not specified. It can either rotate in this direction or either that direction. But one thing we know, the tangential velocity at the end B will be perpendicular, right? Okay. So now let's consider the link QB, right? So now when you're going to consider the link QB, I will sketch it here, right? So now this is the link QB, right? So in this link QB, the specified direction of rotation is unknown because it can either rotate in this direction or it can either rotate in that direction. So but anyhow, one thing we can very clearly say, the tangential velocity at the end B will be perpendicular to this link, even though the direction is unknown, right? So no problem, because that end Q we have already located. So that means this end Q can be considered as a center, right? So now again focus the velocity diagram that you have sketched, right? So you have end Q there, right? Okay. So now carefully focus. Okay, right. So now this is the link QB, right? This point Q can be considered as the center for this link QB. So the tangential velocity at the end B will be perpendicular to this link. It can either go in that way or either go in other way, but it is unknown. So then locate that point or locate that sketch towards there, right? Because this length, this sketch must be perpendicular to this link. So now you can sketch it like that. So now here you can clearly notice something, right? So look at here. So now the tangential velocity AB, you can sketch by a line like that because the specified direction is unknown. The tangential velocity for the link QB can be sketched like that because originally the direction is unknown, but now you can see only at one particular side only you will get the intersection, right? Because after extending this end Q and after extending this end A, right? So both these links AB and QB must get intersected and it must form this end B. So like that, the same scenario should happen in the velocity diagram also, right? That means if you consider the tangential velocity of AB along this direction, and only if you consider the tangential velocity of the link QB along that direction only, you will get the intersection, right? So now you can sketch that. See, if you consider this direction only, you can have the intersection and you can have the point B, simple B. See, now point B is located, right? You got it? Okay. And what else? Okay, so now let me teach you about another story, right? So now consider this piston T, right? So this piston T is moving in a vertical path, right? But still you don't know whether it moves in upward direction or whether it moves in downward direction. Still you don't know that, right? But anyhow, piston T follows a vertical path with respect to the ground, right? Ground means let's say G. So G means ground, right? So now ground is also a point that is at rest. So again you can share this point to denote ground, right? O, P, then G. So now the direction of motion of this piston T is following a vertical path. So piston T follows a vertical path with respect to this ground. As you don't know whether it goes in upward direction or downward direction, you can sketch it by a line, right? Later we can get a specified direction for that. So far, up to now, let's sketch a line like that, okay? Right. So now consider this link BT. Now here you can very clearly see this link BT is the link that we used to connect this piston T to this end B, right? So that means you can have a tangential velocity at the end T with respect to this end B, where the tangential velocity is perpendicular to this link, but the exact direction is unknown, right? That is BT. So you have already located the point B, right? So the tangential velocity must be perpendicular to this link, right? See this link, it must be perpendicular. So sketch that perpendicular line starting from the end B. It can either go in this direction or it can either go in that direction, right? So sketch the line like this, right? So now you can very clearly see when you are going to consider the tangential velocity along this direction only, it will intersect with the path of the piston T, because this is the path of piston T, right? Path of piston T, right? So if you consider the tangential velocity of the link BT in this way only, it will get intersected. So then what is this point? So this point is T, right? So this OT, right? OT is the linear velocity of this piston T. with respect to earth. You can either call OT or GT, but better call GT because the velocity of this piston is defined with respect to the ground, right? So GT, right? So this line, you can see this line indicates the uh, linear velocity, right? Linear velocity of the piston, right? Now this piston is not following any tangential velocity, right? This piston is following a linear velocity that is acting all on the upward direction. So then what is this TB? This TB is the tangential velocity of the link BT, right? So that is directed from B to T, right? Because B is the center, right? So that part also okay, right? So then the next part, right? So now carefully focus. So now here you can see this piston D is connected to this major link AB by using this supportive link CD to a distance 40 millimeters from this end A, right? Because point C is located 40 millimeters away from this end, right? So then what is the ratio? The total length of this link is 70 and this length is 40. So the ratio is 40 divided by 70, right? So now carefully focus. This tangential velocity component AB you already know, right? See, this is AB, right? And that is no problem, right? So you can measure this length, right? I don't know what is that exactly, but according to my answer script, I can say that if you do this neatly, the length of AB is I have obtained 61 millimeters, right? Right, from the velocity diagram, okay, velocity, that means tangential, okay, right, that tangential velocity AB is actually measured as 61 millimeters, right? That means how to locate the point C? That means 61 multiplied by 40 divided by 70, right? That is how you form the ratio. That means it is 34.8. So let's consider as 35 millimeters. Okay, you got it? So now measure 35 millimeters from the end A, right? Measure 35 millimeters from the end A. So let's say it is here, right? So what is this point? C, right? Because you have to consider the same ratio based upon how point C is formed in the configuration diagram. So that same ratio must be adapted in the velocity diagram also. So you know how to form that. So now this is the position of the point C, right? Okay. So now what can you say about the piston D? Now piston D also follows a vertical path, right? Piston D is following a vertical path with respect to the ground, right? So no problem. Now already we have the ground there, right? So now I think in order to sketch piston T, I will use a different color, right? So anyhow piston D, right? See, anyhow piston D follows a vertical path, but still the exact direction is unknown. So I will sketch a line, some dotted line, right? Right, and point C is known, right? So now consider this link CD, right? As the point C is known, you can consider point C as a center, right? Then consider this link CD, right? So if you consider the link CD, there will be a tangential velocity at the end D, right? In such a way that tangential velocity is perpendicular to this link CD. I will sketch it here. So now here we have the link CD, right? There will be a tangential velocity at the end D, right? That is perpendicular to this link, but the exact direction is unknown because we don't know whether it moves in this direction or whether it moves in that direction. The tangential velocity is perpendicular, right? Like that. It's perpendicular. So sketch that perpendicular line, right? It must be perpendicular. So see, now like that you can project it, okay? See, you can project it up to point C, right? So this is how you should sketch it. So now you can project that line that denotes the tangential velocity. Now here you can very clearly see something. If you consider the tangential velocity component along this direction only, it will intersect with the path of piston D. What is this? This is the path of piston D, right? So if you consider this direction only, it will get intersected, right? So what is this? What is this CD? This CD is the tangential velocity of the link CD. So what is this one? What is this one? This indicates that is GD, right? GD, this length, right? So this length GD represents the linear velocity of the piston D, right? See this GD, right? So now that is also okay. So now the same scenario you can consider for the piston S, right? So now here you can see that piston S is connected to this link QB by using the supportive link RS. So now the next target is how to locate this point R, right? So no problem. Point R is located 20 millimeters away from the end Q. This is the link QB, right? So now there is a point called R, right? So this R is 20 millimeters away from the point Q. And what is this length? That is 80. The total length of this link is 80. So what is the ratio? 20 divided by 80, right? So from the velocity diagram, QB is measured as, okay, so let me check the answer from my diagram. The length QB from my velocity diagram that I have sketched according to the scale is 37 millimeters. Right? So what is this length QB? 37 millimeters. So as according to the ratio, in order to locate this point R, so QR must be 37 multiplied by 20 divided by 80. So what will be that length? 9.25 millimeters, right? So let's consider 9 millimeters, right? So measure 9 millimeters, right, from the end Q. Okay, measure 9 millimeters from the end Q. So let's say here, so this is the point R, right? Okay, so that is the point R. Okay, so now what is this length? 9 millimeters, right? Okay, and now the next thing, consider this piston S. Now this piston S follows a horizontal path with respect to the ground. So I will sketch it like this. So now this is the ground. Okay, so still you don't know along what particular direction that this piston travels, right? Whether it goes towards right or whether it goes towards left, you don't know that. So let's sketch that path of the piston S. Anyhow, the path of piston S is horizontal with respect to the ground. So let's sketch a dash line like that, right? Okay, no problem, right? So now consider this link RS, right? Link RS. Now this point R, the position R is already known, right, as a well specified point. So you can define the tangential velocity at the end S with respect to R. If you're going to consider this link RS, right, there will be a tangential velocity where the exact direction is unknown, but you can define it by Vs simple R, VSR. Tangential velocity at the end S with respect to R, right? Okay, so now see, the tangential velocity must be perpendicular to this link, right? Anyhow, it must be perpendicular, right? Right. So this perpendicular you can project there. See, perpendicular, right? So now this line represents that tangential velocity. Till you don't know whether it goes in that direction or that direction. So let's sketch that. So now you can very clearly observe that when you are going to consider the tangential velocity along this direction only, it will intersect with the path of piston S. So what is the correct direction? So what is the correct direction of the tangential velocity of the link RS? It is this direction, right? Otherwise, if you're going to consider this direction, it will not intersect with the path of piston S, right? What is this one? GS. See, GS. V velocity, the linear velocity of the piston S with respect to ground. So this represents the linear velocity of the piston S. That means piston S moves along the left direction, right? So now you can complete it, right? So that will be the answer. Now you can compare the diagram that I have sketched and the velocity diagram that I have sketched according to the scale, right? See, this is matched, right? Is it clear? Yeah. I will adjust some space, right? See, this is the marking scheme, right? See, all are matched, right? Okay, so now we are going to find the linear velocities of all the pistons and the angular velocities of all the links, right? So first I will start with the piston S, right? So now you know this piston S follows a horizontal path, right? So this is the velocity diagram that I have sketched, right? And also I will show you my marking scheme, right? Because in the marking scheme the velocity diagram that I have sketched is a different one, right? So all the lengths that I have considered are the ones that I have taken from the velocity diagram as according to my marking scheme, right? So now in order to find the linear velocity of this piston, right? So what we have to do, we need to measure the distance between the point G and S, right? Because now previously I have taught you that this point O, point P and G, right? G represents ground, right? So in order to locate these 3 points, right, we use the same point because those points are at rest, or those points are our reference points, right? So now I will tell you the respected length, right, as according to my marking scheme, okay, right? So this is the velocity diagram. So now we are going to find the linear velocity of piston S, right? So I will write it here. Linear velocity of piston S, right? So that velocity is actually the length that you have measured from the velocity diagram. That means this length S to G, that length. So according to my marking scheme, that length is 55 millimeters, right? But you know, as according to our scale, right, as you can remember, initially I have taught you that we use 40 millimeters to denote 2513.3 millimeters per second. You know that. So that means our actual velocity will be this value divided by 40 multiplied by 2513.3, right? So what is the answer? 3455.8 millimeters per second, right? Or in other words, you can say 3.4558 meters per second, right? So that doesn't matter, right? So then we can move to this piston, right? The piston T that follows a vertical path, right? Okay, so what can you do for that? So in order to find the velocity of the piston, linear velocity of the piston T, you need to measure the distance between the point G and T, right? Because point T is located here, right? That means length between the point T and G, right? Okay. Marking scheme, right? So according to the marking scheme, that length is 21 millimeters, right? So then you can say linear velocity of piston T. So what is that? The respected length 21 millimeters, right? And that scale factor, this divided by 40 multiplied by 2513.3. The answer will be 1319.5 millimeters per second. That means 1.319 meters per second, right? So this is not necessary. You can even keep the answer at here, right? Okay, right. So what is the next thing? So next we can find the velocity of the piston D, right? So now you know piston D also follows a vertical path, right? So again go to the respected velocity diagram, right? So how can we locate uh, the necessary points, right? So in order to find that velocity, you can measure the distance between the point G, because point G is here, right? You can either call that point O, that doesn't matter. So you need to measure the length between this point and this point, right? So because this point is the point that represents simple D, right? Here to there, right? So as according to my marking scheme, linear velocity of piston D, right? So I have obtained 25 millimeters from my velocity diagram, then that divided by 40 multiplied by 2513.3, value would be 1570.8, that means 1.57 meters per second, right? Okay, so I will also show you my marking scheme, right? So this is the diagram that I have sketched in order to teach you how to sketch, but actually this is the velocity diagram according to my marking scheme, right? So now you know point O, P, and also point G. Okay, better say, is there any other point named as G? No, let's say simple G. Point G represents ground, right? You know that. So in order to find the velocity, linear velocity of piston S, you measured this distance, right? The distance between point G and S, right? Because I thought it is much better to show you the marking scheme also, G to S, right? So in order to find the piston, the velocity of the piston T, you can measure the length between point G and T here, right? So now you can see to what particular direction this arrow is pointed, right? G to T, it's here, this distance, right? Okay, so according to my marking scheme, this distance is 21 millimeters, and this distance G to D is 25 millimeters. This distance 55 millimeters, right? So now I think that part is okay. Now you know how to find the linear velocities of the pistons, right? Okay, right. Okay, so now let's calculate the angular velocities, right? So basically we have to calculate the angular velocity of link AB, then link QB, and then link CD, then link BT, and finally link RS, right? So now let's consider how to calculate the angular velocity of the link AB, right? So first, by using the velocity diagram that you have sketched, you can find the tangential velocity of the link AB, right? So now what is the tangential velocity of the link AB? So first you have to locate AB, right? So this is AB, right? A to B, right? So that means first you need to measure the length, right? AB, right? So according to the marking scheme, right? That means previously I have shown you that I have sketched a separate marking scheme, right? So now this length AB indicates the tangential velocity of the link AB, right? So that length is 61 millimeters, right? So how to find the angular velocity? We know the tangential velocity equals r omega, right? This r is nothing but the length of the link. That means if you are going to consider for links, it is the length of the link, right? But of course if you are going to consider for a crank, that is the crank radius, right? But here it is the length of the link, right? So now what is the angular velocity of the link AB? Let's write it. Angular velocity of the link AB, right? So that is the length, right? That is measured from the velocity diagram, right? So this is the marking scheme. So you need to measure this length AB, right? So it is 61 millimeters, right? So then you have to divide by that, that we are going to consider the scale, right? Divide that by 40 millimeters, right? Because as I have told you earlier, 40 millimeters are used to denote 2513.3 millimeters per second, right? So first divide this by 40, then multiply by 2513.3, right? So this will ultimately give the respected tangential velocity, right? So if you further divide this value by the length of the link, right? See, this is the length of the link, right? AB. So what is that length? 70 millimeters. So if you divide this by 70 millimeters, right? So then you can find the angular velocity. So what is that? 54.8. Remember the units, radians per second, right? So it is not rpm, right? So because if you are going to consider this formula v equals r omega, you will get the final answer in radians per second, right? Okay. So then let's consider the angular velocity of the link QB. So now this is the link QB, right? QB. So as according to the velocity diagram that we have sketched, right? So you have to locate where is QB, right? So the distance between these 2 points Q and B, that indicates the tangential velocity of the link QB, right? This length. So you can keep the ruler there. So you can measure, basically you can measure the length QB, okay? So according to the marking scheme, the length of tangential velocity component QB is 37 millimeters, right? So let's write it again, right? Let's write it, right? Let's do it for some links. Angular velocity of the link QB, right? So first you have to consider the length. So what is that length? It is 37 millimeters, right? And 40 millimeters are used, right, to denote 2513.3, right? So this part will give you the tangential velocity. So you divide that by the length of the link QB, which is 80 millimeters, right? So then what is the answer? 29.1 radians per second, right? So now you know how to continue that. So like that, anyhow, I will tell you what are the lengths, right, that are measured from the velocity diagram, right? So then you can calculate. So if you are going to consider the angular velocity for the link CD, that means you have to measure the tangential velocity from the velocity diagram, right? So what indicates the length CD, right? CD is there, right? The length between the point C and D, right? So you need to measure this length CD, right? So then I think it's better here I will write it from the velocity diagram. Length of CD, what are the other lengths? Length of RS, length of BT, right? I will tell you what are the lengths. The length of CD according to the marking scheme is 36 millimeters, right? So after when you have sketched, you can match with my values, right? So for the link RS, what is RS? So RS, so point R is here, right? Because point R is located in between point Q and B, right? You know that. So what is the length of RS? You can measure the length from this point R to this point S. So because now I'm referring the marking scheme. So length RS is 56 millimeters, right? 56 millimeters, right? So now the final link is link BT, right? This link BT, right? So now by referring the velocity diagram, so what is the length of BT? BT will be here, right? This length, the length between the points B and T. So according to the marking scheme, what is that value? 19 millimeters, right? BT 19 millimeters, right? 19 millimeters, right? So now you know the length, so you can multiply that by the factor, right? So now I will directly tell you what are the angular velocities, right? So here I will write the angular velocities. Angular velocities, right? The units are radians per second, right? Okay. For link CD, because no need to waste time on that, you know how to do that. So for link CD, it is 56.5 radians per second. Link RS 35.2 radians per second, and for link BT it is 29.8 radians per second, right? So now you know how to find the angular velocities of all the links and also the linear velocities of all the pistons, right? Okay, so that's it.